Rare minerals have become the most strategic industrial resources of the 21st century because they are essential for energy storage, electrification, and advanced computing. Electric vehicles require lithium, nickel, cobalt, and copper at volumes that have never been used in previous industrial cycles. Wind turbines, solar farms, and industrial automation systems depend on rare earth magnets made from neodymium and dysprosium. Artificial intelligence chips require materials such as silicon, gallium, and germanium, making mineral access a core requirement for the digital economy. The country that controls rare mineral extraction, refining, and logistics may gain long-term industrial advantage. China currently dominates the global rare mineral ecosystem because it invested heavily in mining, transportation, and advanced processing technologies. This dominance was not accidental, but the result of a strategic decision to treat minerals as a national security priority. The United States, Europe, and Japan are now realizing that industrial production cannot scale without stable mineral supply. Electric vehicle factories require long-term mineral contracts because every battery pack needs large quantities of lithium and nickel. Semiconductor plants depend on purified mineral inputs because chip manufacturing cannot function without advanced chemical refinement. Global demand for lithium may increase more than 40 times in the next 2 decades because electrification requires massive energy storage. Copper demand is rising rapidly because every electric motor, power grid, and renewable installation requires copper wiring. The world has not developed enough new copper mines to satisfy electrification goals, and experts warn that shortages could slow clean energy adoption. Rare earth minerals are heavily concentrated in China, even though raw extraction also occurs in other regions. The most profitable segment of the mineral value chain is not mining, but chemical processing, metallurgical engineering, and industrial qualification. China invested early in refining capabilities and built a vertically integrated supply chain for rare earth magnets. This allowed Chinese companies to dominate pricing, export leverage, and innovation in renewable energy systems. Western economies outsourced industrial capacity for decades and are now struggling to rebuild mineral supply chains. Mining projects take more than 10 years to develop because environmental regulations and logistical planning require long approval cycles. Refineries require specialized labor, industrial chemistry, and stable energy access to operate at scale. Mineral security has become as important as oil security because electrification, robotics, and chip production depend on mineral resilience. India, Brazil, Indonesia, Canada, Australia, and Mexico possess large mineral reserves that are becoming central to international diplomacy. These countries are negotiating long-term supply agreements with industrial powers to ensure stable access to battery-grade materials. National resource alliances are forming around mining, refining, technology transfer, and industrial co-investment. Mineral diplomacy will shape trade policy because electric mobility requires raw materials the same way vehicles once required oil. Financial markets are beginning to treat rare minerals as strategic assets rather than traditional commodities. Mineral scarcity could impact inflation, industrial pricing, and long-term monetary stability. Governments are developing strategic stockpiles to stabilize domestic production and prevent supply shocks. Battery manufacturers are forming vertical partnerships with mining companies to secure raw materials for electric mobility. AI hardware manufacturers are evaluating material access as a critical competitive variable for advanced chips. Rare minerals are becoming the industrial foundation of clean energy, robotics, and aerospace systems. Semiconductor fabrication plants require ultra-pure germanium, silicon, and gallium for quantum computing experiments. The mineral race is shaping national security because advanced defense systems require rare earth magnets and precision sensors. Mineral access affects industrial independence because production cannot scale without stable raw materials. Countries that underestimate mineral risk may lose economic competitiveness as manufacturing relocates toward material-rich regions. China's investment in mineral supply chains gave it leverage in electric vehicle production, energy storage, and renewable infrastructure. Many nations are attempting to diversify supply away from China to avoid strategic dependency. Europe is implementing critical mineral strategies to localize refining capabilities and reduce import risk. The United States is expanding domestic mining and refining under industrial policy initiatives and green energy legislation. Rare mineral refining is the most complex stage because chemical purity determines industrial performance. The world cannot electrify transportation without massive increases in lithium extraction and battery-grade refining. Copper shortages may disrupt renewable energy grids because power systems require extensive copper wiring. Nickel production is expanding in Southeast Asia, but environmental standards and industrial quality remain uneven. The clean energy transition depends on stable mineral access, high-quality refining, and long-term supply planning. Without mineral security, electrification projects could become more expensive, slower, and difficult to scale. Technological leadership is shifting toward countries that treat mineral ecosystems as industrial infrastructure rather than commodity markets. Rare earth magnets are essential for industrial motors, wind turbines, electric aircraft, and precision robotics. Permanent magnet manufacturing is a strategic capability because it enables industrial automation and high-performance electrification. Mineral science is becoming a national research priority because material innovation determines industrial competitiveness. New battery chemistries will require sodium, lithium, solid-state conductors, and hydrogen-compatible materials. Quantum computing will rely on minerals with extreme purity standards that require advanced engineering. AI production capacity increases mineral dependency because computational infrastructure requires industrial hardware. AI chips cannot function without rare minerals, so material availability becomes a core component of digital sovereignty. Countries are realizing that software and data-driven platforms cannot exist without physical material infrastructure. The next phase of industrial competition will depend on mineral optimization, energy efficiency, and automation. Financial resilience depends on stable mineral supply because industrial pricing affects inflation and trade balance. Electric vehicle adoption depends on affordable battery materials, which depend on mining and refining capacity. Renewable energy adoption depends on permanent magnets, copper wiring, and advanced power electronics. Semiconductor expansion depends on industrial chemicals, mineral purity, and supply chain reliability. Mineral shortages could slow digital manufacturing because industrial automation requires materials for motors and sensors. Global mineral access gives countries leverage in trade negotiations and industrial diplomacy. The world is entering a period where mineral productivity is more important than oil productivity for industrial competitiveness. Mineral ecosystems are difficult to replicate because they require long-term investment, skilled labor, and research institutions. Industrial capacity cannot scale without reliable raw material access and consistent environmental standards. The clean energy sector needs mineral security for grid-scale batteries, hydrogen systems, and electric transportation networks. Mineral scarcity is influencing national budgeting, industrial strategy, and international trade policy. Countries are forming joint ventures to extract minerals, develop refining capabilities, and share technology. Geopolitical alliances are emerging along mineral supply corridors that integrate transportation, refining, and manufacturing. Capital markets are investing in mining firms, battery firms, and semiconductor firms as mineral demand accelerates. Rare mineral prices could remain volatile due to underinvestment in extraction and processing capacity. Industry leaders fear that mineral shortages may delay electrification targets and industrial decarbonization. Technological ecosystems must integrate supply chain resilience with energy security to remain competitive. Governments are monitoring mineral supply as a strategic vulnerability for national security planning. Defense manufacturing requires precision materials that cannot be substituted easily. Industrial robotics requires magnetic materials, advanced motors, and high-performance electronics. Mineral access affects aerospace innovation because satellites, rockets, and avionics require specialty materials. Economic power may shift toward nations that combine mineral resources with industrial engineering and automation. Mineral diplomacy will determine the location of manufacturing hubs because production needs stable supply. Renewable energy companies are competing for scarce mineral contracts to ensure industrial continuity. Major automakers are restructuring supply chains to secure long-term mineral rights. Mining companies are becoming more influential in financial markets because mineral scarcity increases valuation. Technological sovereignty requires coordinated policies for mining, refining, and industrial strategy. The mineral race will determine future supply chains for electric mobility, AI hardware, and quantum systems. National energy transitions cannot be completed without mineral access for grid modernization. The next global industrial revolution will be defined by mineral analytics, material engineering, and energy optimization. Nations capable of refining minerals locally gain pricing power and industrial leverage. Mineral refining determines export advantage because processed materials are more valuable than raw extraction. The semiconductor industry depends on mineral purity because chip defects originate at the material level. Financial analysts are treating mineral markets as long-term strategic indicators rather than short-term speculation. Central banks may hold mineral reserves in the future if mineral scarcity influences currency stability. Industrial automation will accelerate mineral consumption because robotics increases productivity and device density. Governments are integrating mineral security into national industrial policy frameworks. Countries that fail to secure minerals may lose global competitiveness in electrification and computing. The clean energy economy will depend on mineral innovation and refining efficiency. Digital manufacturing requires mineral resilience for motors, electronics, and industrial automation. Mineral supply chains are becoming a cornerstone of financial planning, trade negotiation, and industrial diplomacy. Nations are forming alliances to build mineral infrastructure and stabilize future production capacity. Industrial prosperity will depend on stable mineral access, advanced material science, and long-term planning. The mineral war is not a temporary trend, but a structural transformation of global industry. The financial power of the next century will belong to countries that control minerals, electrification, automation, and industrial computing.